Good day to everyone. My name is Chang Ying with Matrics number XS356, supervised by Dr. Chu Chan. I am a final year student from the Faculty of Computer Science and Information Technology, University of Malaysia, Sarawak. Today, I'm going to present the first phase of my final year project entitled Detecting Phishing Email Using Deep Learning. In this presentation, I will walk you through the research foundation, the literature review of current technologies, and the detailed methodology I have designed to develop an effective detection system. Email remains the most common and effective delivery channel for phishing attacks because it is widely used for professional, financial, and personal communication. Attackers exploit users' trust in email to steal credentials and sensitive information. In the recent years, phishing emails have become more sophisticated due to the use of artificial intelligence. Conventional detection techniques such as the rule-based, heuristic, and blacklist approaches rely on predefined patterns and known signatures. As a result, they are ineffective against zero-day attacks. This shows the need for more advanced detection methods that can understand the meaning and intent of email content. Moving to the problem statement, traditional systems such as the rule-based and blacklist method are increasingly falling against zero-day attacks. Because these methods rely on static patterns, they struggle to identify modern or AI-generated phishing emails that use contextual language to bypass the filter. Other than that, machine learning models such as the random forest or SVM depend on manual feature engineering. This process is not only time-consuming, but also fail to capture the complex, nonlinear linguistic patterns. Finally, even though high-performance enterprise solutions exist, they are often costly, inaccessible to individual users. There is a need for a lightweight, transparent, and high-accuracy tools that bridge the gap between the enterprise security and the everyday user. The main aim of this project is to investigate and evaluate deep learning approaches for detecting phishing emails and to identify the most effective models. The first objective is to apply deep learning techniques to accurately classify emails as either phishing or legitimate. The second objective is to evaluate and compare the model's performance using standard evaluation metrics such as accuracy, precision, recall, and F1 score. And lastly, the objective is to develop a web-based phishing email detection application. Next, I will outline the scope and the significance of this research. We focus on text-based phishing detection, analyzing subject line and body content. The dataset is publicly available from Kaggle. All technical development is conducted within the Python ecosystem using specialized deep learning libraries. The final outcome is a lightweight web-based prototype that serves as a proof of concept for real-time detection. As for the project significance, this work carries weight for two main groups. For the individual user, it provides an accessible tool to identify phishing emails. For organization, this research helps to reduce the security risk. This section presents an overview of existing research on phishing email detection techniques. Early studies mainly rely on rule-based and heuristic methods, which detect phishing emails using predefined rules and known patterns. Even though these approaches are simple and efficient, they struggle with adaptability and zero-day attacks. To overcome these limitations, researchers introduced machine learning-based approaches that learn patterns from the data. This method improves the detection accuracy but still depend on the manual feature engineering. In more recent research, it focuses on deep learning and transformer-based models, which can automatically extract complex features and understand contextual language patterns in email. These approaches have demonstrated significantly higher accuracy in phishing detection. Traditional phishing detection methods rely on predefined rules, heuristics, and blacklists. These systems are fast and simple, but they are highly static and cannot adapt well to new or evolving phishing techniques. As a result, they often fail to detect zero-day attacks. To address this limitation, machine learning-based approaches were introduced. These methods extract features from email content, headers, URLs, and metadata, and then apply classifiers such as SVM, random forest, and naive Bayes. Machine learning techniques platform is better than rule-based system because they learn pattern from data and can detect previously unseen phishing emails. However, their effectiveness depends heavily on manually engineered features. This manual feature extraction process is time-consuming and may fail to capture complex semantic relationships in modern phishing emails. Deep learning approaches overcome many of the limitations of traditional machine learning methods. Unlike feature-based models, deep learning can automatically learn meaningful representations directly from the raw email text. Convolutional neural networks, or CNNs, are effective at capturing local patterns, such as suspicious keywords or phrases commonly found in the phishing emails. Recurrent models like LSTM and GRU are designed to handle sequential data, making them suitable for understanding the flow and the structure of email content over the time. And more recently, transformer-based models such as BERT have shown strong performance due to their bidirectional contextual understanding of language. However, this model vary in terms of accuracy and computational cost, which motivate the need for a systematic comparison to identify the most suitable model for a real-world phishing email detection. Based on current studies, CNN models achieve good performance with relatively low computational costs and fast training time. They are effective in identifying suspicious keywords and local phrase patterns. LSTM and GRU models outperform CNN by capturing sequential information within the emails. LSTM achieve high accuracy but require more computational resources, while GRU provides a similar performance with improved efficiency. BERT demonstrates the highest accuracy. However, this comes at the cost of very high resource consumption and longer training time. Therefore, this comparison highlights a trade-off between detection performance and computational efficiency. And this motivates the need to identify an optimal model for practical development. Moving to the overall methodology framework used in this project, the methodology is divided into 7 main phases, starting from data selection until the web application development. Phase 1 is data selection, where a phishing email dataset from Kaggle is selected as the main data source. Phase 2 is data preprocessing, which includes handling missing value and duplicates, noise removal, cache normalization, and stop word management. Next, phase 3 is feature extraction, transforming text into numerical representation. And phase 4, data splitting. The dataset is divided into training, validation, and testing sets. Moving to the phase 5 is model training, where our 4 deep learning models are trained using the same dataset and settings. After that, phase 6 is model evaluation, which use confusion metrics and evaluation metrics such as accuracy, precision, recall, and F1 score to compare model performance. And finally, phase 7 is web application development, where the best performing model will be integrated into a web-based phishing detection system. The dataset is obtained from Kaggle and is curated by Nasser Abdullah Alam and Amif Kandalkar. It contains over 82,000 email samples, which are already labeled as either phishing or legitimate emails. Moving to the data pre-processing phase, which is a crucial step before the model training. First, the missing value and duplicate emails are identified and handled to avoid bias in the dataset. Next, noise removal is applied by eliminating unnecessary characters such as symbols, HTML tags, and extra spaces. Then, case normalization converts all the text to a lowercase to ensure consistency in word representation. After that, stop word management is performed to reduce irrelevant words that do not contribute significantly to phishing detection. And finally, sequence padding is applied to ensure all email tags have the same length, which is required for the deep learning models like CNN, LSTM, and GRU. Moving to the feature extraction phase. Feature extraction is the process of transforming pre-processed email text into a numerical representation that can be understood by deep learning models. Unlike traditional machine learning methods that depends on manual features engineering, this project focuses on automated representation learning, allowing the models to learn meaningful patterns directly from the data. For CNN, LSTM, and GRU models, static word embedding are used. The email text is first tokenized, and each word is mapped to a dense vector representation. This embedding captures semantic relationships between words, enabling CNN models to detect local textual patterns, while LSTM and GRU models learn sequential dependency within the email contents. For the BERT model, contextual embedding are applied using BERT's word piece tokenization and p-trend embedding layers. Unlike the static embeddings, BERT generate context-aware representations, where the meaning of each word depends on its surrounding context. The dataset is split into three subsets using a 70-15-15 ratio. The 70% training dataset is used for the models to learn the underlying patterns that distinguish phishing from legitimate emails. The 50% validation set is crucial during the training phase to tune hyperparameters and monitor for overfitting. And finally, the 50% of testing set is kept completely unseen until the final evaluation to reflect how the system will perform in a real-world scenario. And I also apply stratified sampling during this process to maintain a consistency class distribution across all subsets. This is to prevent biased result to ensure that both phishing and legitimate emails are represented proportionally. Moving to the model training phase, which is the core component of this project, deep learning models learn to distinguish between phishing and legitimate emails by optimizing their internal parameters using label data. 4 models are trained in this study, which is CNN, LSTM, GRU, and BERT. To ensure a fair comparison, all models are trained using the same training sets and validate using the same validation set. And since this is a binary classification task, binary cross-entropy is used as the loss function, while accuracy, precision, recall, and F1 score are used for performance evaluation. The models are implemented using TensorFlow and Keras, with the Hugging Face Transformers library specifically used for the BERT model. The CNN models focus on capturing local textual patterns, such as suspicious phrases, using convolution and max pooling layers. The LSTM model is designed to capture long-term dependencies in email text, making it effective for modeling narrative flow. The GIU model follows a similar approach to LSTM, but a simpler getting mechanism, resulting in faster training and lower computational costs. And finally, BERT is a transformer-based model that uses bidirectional self-attention to understand the full contextual meaning of email content. A P-trend BERT model is fine-tuned for phishing classification. This enables for a better detection of semantic intent and zero-day phishing attacks. And together, all these models allow a comprehensive and fair comparison of different deep learning architects for phishing email detection. Moving to the model evaluation, a quantitative evaluation framework is used to compare the performance of CNN, LSTM, GIU, and BERT. All models are evaluated using the same unseen testing dataset, ensuring the fairness and consistency in comparison. A confusion matrix is used to analyze classification errors. This includes the true positive, true negative, false positive, and false negative. In a cybersecurity context, false negative, where phishing emails are missed, are the most critical errors and are carefully analyzed. And several performance metrics are computed, including the accuracy, precision, recall, and F1 score. And F1 score is selected as the primary benchmarking metric due to its balanced consideration of false positive and false negative. In addition to classification performance, the latency analysis is conducted to measure inference time per email. This is to ensure the selected model is suitable for a real-time deployment in the web-based phishing detection system. And finally, we implement the best model into a web-based application to turn our research into a practical tool. This application allows for manual submission of email tags, which the model then classifies in real time as either phishing or legitimate. To help users understand the reliability of the result, we display a confidence score. We have also integrated a feedback loop so users can report errors, helping us to refine the model further. For oversight, the application features an administrative dashboard. This allows authorized personnel to monitor system-wide statistics and review the detailed detection logs to ensure the system remains effective against new threats. And now, I will walk you through the actual interface design. The home page is designed for accessibility. It features a central text area where users can manually type or paste the full content of an email they wish to scan. To ensure the ease of use for non-technical individuals, there is a clear Analyze button to initiate the deep learning process. Once the analysis begins, the user is presented with this loading screen. Behind the scenes, the backend server is performing text pre-processing, including like cleaning, tokenization, and padding, before feeding the encoded input into the active detection model. This is to provide a visual feedback that the system is actively processing the request. If the email is safe, the system displays a legitimate classification, and a confidence score is displayed to help the user to understand the confidence of the model's predictions. Conversely, if the model detects a threat, a phishing result is displayed in red to grab the user's attention. Along with the high confidence score, the system provides a clear warning: do not open any links or attachments, and delete it immediately. And this is the user feedback page, which is the vital for system reliability. If a user believes the model made an error, either a false positive or a false negative, they can report it here. They can also provide optional comments to explain why the classification failed incorrect. To protect system integrity, administrative functions are restricted. The admin login page requires a secure ID and password. This is to ensure that only authorized personnel can access. Once logged in, the administrators sees the dashboard. This page visualizes the system health using key metrics, for example, the daughter number of emails analyzed, the current phishing detection rate, and the volume of user feedback. It also concludes a trend chart to monitor daily activity and a list of recent high risk detection. The detection logs page provides a comprehensive searchable record of every analysis performed by the system. Each log entry includes the classification label, confidence score, and a timestamp. And finally, the feedback management page allows the admin to review the reports submitted by the users. This interface shows the original classification versus the reported one, along with the user comments. To conclude, Phase 1 has successfully established the project foundation. I have completed the comparative study of deep learning models and finalized a system framework ready for development. Moving into FYP2, the focus will be on technical implementation. I will train and compare the selected architecture to identify the most accurate model. And this model will then be integrated into the web prototype I have designed to provide a real-time phishing detection. And the ultimate goal is to deliver a practical tool that helps individual users to identify threats more effectively. And that concludes my presentation on the planning and design phase of my project. Thank you.